I'm Rajesh Uppal, Director IDST. We bring sharp insights and foresight on defense, security, and emerging tech. Let's dive in.
If you've ever wondered what truly makes the world tick, what drives the air we breathe, the medicines that heal us, or the materials inside your phone, there's a field quietly shaping all of it. And it works on a scale so small, we'll never actually see it with our eyes. Welcome to quantum chemistry, the science that explains how the universe builds itself, molecule by molecule. It's a field where chemistry meets quantum physics, and the results are nothing short of extraordinary. Instead of watching how large batches of chemicals behave in a lab, quantum chemistry dives straight into the realm of atoms and electrons. It asks, why do molecules form the shapes they do? Why do some reactions happen instantly, while others need a push? And how can we predict all of this before running a single experiment? At the heart of this science is a surprisingly simple idea. Electrons don't behave like tiny balls orbiting a nucleus. They behave like waves, spread out, interacting, shifting, and influencing one another in ways classical physics simply can't capture. To describe this strange behavior, scientists use the Schrödinger equation. Now, you don't need to do the math, but think of it as a formula that reveals a molecule's energy landscape. It tells us where electrons prefer to live, how strongly atoms bond, and what shapes molecules naturally settle into. Everything that happens in chemistry, every bond, every color, every reaction, starts right there. Once you understand electron waves, you get something incredibly powerful, the ability to predict chemistry. Wave functions map out the entire quantum state of a molecule. Molecular orbitals show where electrons like to gather. And electron correlation, how electrons subtly avoid one another, tells us why some molecules are stable while others fall apart instantly. These aren't just theories. They're tools that let us peer into the quantum world with astonishing accuracy. But here's the catch. Solving these equations is brutally hard. For anything larger than a hydrogen atom, the math becomes overwhelming. That's where computational chemistry steps in. Using advanced algorithms and high-performance computers, scientists can now simulate molecules containing hundreds, sometimes thousands of atoms. They can mimic reactions, study drug behavior, or explore new materials long before they're synthesized in a lab. Some of the most widely used methods have become legends in the field. Density functional theory, DFT, is the workhorse for big systems, letting us estimate electron behavior efficiently. Hartree-Fock gives us a starting point by treating electrons as independent waves. And for extreme accuracy, Quantum Monte Carlo uses statistical sampling to crack problems conventional methods struggle with. All of these methods live inside powerful software like Gaussian, Orca, and games, which have quietly shaped countless breakthroughs over the past decades. And the real excitement? High-performance computing is pushing boundaries even faster. Supercomputers like Frontier in the United States can simulate biological systems with quantum precision, something scientists once believed impossible. These machines now model drug-protein interactions, predict molecular stability, and help design therapies for diseases that resist traditional treatments. For the first time, we can study how a drug behaves before we ever make it. It's ushering in a revolution in drug discovery. quantum simulations already help develop HIV protease inhibitors years ahead of schedule. In 2024, researchers in Melbourne performed the first large-scale quantum simulation of biological systems, an achievement that opens the door to precision medicines of the future. The impact goes far beyond healthcare. Quantum chemistry guides the creation of advanced materials, from superconductors and solar cells to flexible electronics and next-generation batteries. Microsoft's hybrid quantum classical platform recently screened over 32 million molecules to discover a promising new battery material. Without quantum chemistry, that search might have taken decades. It also transforms catalysis, environmental chemistry, nanotechnology, and even spectroscopy, where quantum models explain why molecules absorb and emit light the way they do. And there's a new frontier emerging, the fusion of quantum chemistry with quantum computing. Algorithms like the variational quantum eigensolver and quantum phase estimation are already being tested on prototype quantum processors, providing glimpses of a future where we might simulate massive biomolecules in real time. Alongside that, AI is stepping in, trained on datasets like QT to predict molecular properties with remarkable accuracy, sometimes without running full simulations at all. Of course, the journey isn't without challenges. As molecules grow larger, the computational load explodes. Quantum hardware is still error-prone and fragile, and modeling real-time dynamics like bonds breaking during a chemical reaction remains incredibly complex. But the momentum is unstoppable. Every year, algorithms get better, supercomputers get faster, quantum processors become more stable, and AI fills in the gaps, learning patterns that humans took generations to understand. Quantum chemistry is no longer just theory. It's becoming a predictive engine for the next century of innovation. It shapes the medicines we design, the materials we build, the energy systems we need, and even the computers of the future. And as we push deeper into the quantum world, one thing becomes clear. We're not just observing molecules anymore. We're learning to design them, atom by atom, electron by electron, unlocking the secrets of matter and writing the next chapter of science itself. Thanks for watching. Subscribe, follow, or visit IDSTH.com for more cutting-edge defense and tech insights. See you in the next one.